In today's lesson, we are going to continue our review on linear relations. So in our previous lesson, we looked kind of at the basics of what a linear relation is, y equals mx plus b, what the values are, how to graph them, the different types of slope, how to determine the equation of a line. And we're going to continue with that today as well. Again, this is just a review of stuff that you, hopefully you learned in grade 9. Whether you remembered or not is another thing, but hopefully it kind of triggers your memory or gets you to remember some of the stuff you learned. So again, review: y equals mx plus b. That's the equation of a line. Right? M equals our slope. We can also call it our rate of change. Rate of change, the multiplier. Rise over run. Or we might also call it like the delta y over delta x. And we also learned yesterday just another way we could look at it: y2 minus y1 over x2 minus x1. So just another formula for slope. B is our y-intercept, or our constant, our starting value, or starting/initial value. Maybe a base phi, depending on the scenario we're looking at. Right, so those are all the different terms for our m and the b value of our equation of a line. What we're going to look at today is the standard form of an equation. So the standard form is a different form of a linear equation. So it's ax plus by equals c. Now it's different from our y equals mx plus b formula, and it doesn't give us the same information. So when we look at an equation in standard form, we might not necessarily see the slope and the slope and the y-intercept. Right? Now, it doesn't mean we can't get it, but we're not going to take those values as they are and say, oh, this is the slope or this is the y-intercept. Now, we may need to graph them, right, depending on how we're given the equation. So if we're given an equation in standard form, we can graph it in two ways. One is by finding the intercepts. And so what we're going to do is we have an equation, 3x plus 5y equals 15. Now, you might look at that and say, okay, well, one of those numbers is the slope, one is the y-intercept. That's not the case because it's not in standard form. It's not in y equals mx plus b form. So what we can do, though, is find the intercepts. And what we're going to do first is let's find the x-intercept. So the intercept just means the x and y-intercept where it crosses the x and y axis. Right? So the x-intercept, when we talk about the x-intercept, the y value equals 0. Right? So when we talk about the x-intercept, it's somewhere along this axis, and the y value for that point is going to be 0. So what we can do is substitute 0 in for y, and that will allow us to solve for x. So 3x plus 5 times 0 equals 15. I have 3x equals 15 because 5 times 0 is 0, so that disappears. And so we have 3x equals 15. Now I can just go through and solve this one-step equation. 3 times what equals 15? Well, if you don't know off the top of your head, divide both sides by 3. X remains. 15 divided by 3 is 5. So that means our x-intercept is 5. So I can put a point at 5, 0 for our x-intercept. I'm going to do the same thing now, but for our y-intercept. If you might have guessed, our y-intercept is when x equals 0, because it's along the y-axis. So the x value is always going to equal 0. I'm going to do the exact same thing, except instead of making y 0, I'm going to make x 0. So 3 times 0 plus 5 y equals 15. 3 times 0 is 0. 5y equals 15. one-step equation. You could do it in your head. If not, we're going to divide both sides by 5. One side cancels out, and we are left with y equals 3. So that means our y-intercept is 3. So I can put a point here. So it would be the point 0, 3 for our y-intercept. And now I can graph. I have 2 points. Ideally, we would like 3, but 2 when we're dealing in this form. 2, if we're dealing with the intercept method, 2 is strong enough to give us at least enough points or enough information to line it up to draw our line. So that would be roughly what our line would look like for this equation. The second method is converting. So what we would want in this case is to convert it to y equals mx plus b, and then we looked at how to graph these types of equations. Right? We spent a lot of time learning how to graph these equations in grade 9. We looked at that yesterday. So if I can get this equation to this form, hopefully I'll be able to graph it. So what we want to do, we need to have y on one side by itself and everything else on the other side. So I need to move this 3x to the other side. Right? So there's different ways you can think of it, right? You could think of canceling it out on the one side. By canceling it out, I make it the opposite, so minus 3x, but I have to do the same thing to the other side. So minus 3x on one side, one entire side cancels out. I'm left with 5y equals 15 minus 3x. That's one way you could think of it. The other way you can think of it is, well, if I'm taking one thing and moving it across the equal sign, I have to change the operation. It becomes the opposite. So 3x on one side, I move it to the other side, it becomes minus 3x. So 2 different ways you can think of it. So now I have y on one side, I have the values on the other side, but it's not quite the equation y equals mx plus b. And again, the reason for that is because I have a value in front of the y. I have this value here, which I don't want. So I need to cancel that out. So how do I get rid of this 5? Well, think of solving equations. What's happening between the 5 and the y? Well, it's being multiplied. So if I want to cancel out multiplying by 5, I'm going to divide by 5. But in order to keep it balanced, I have to divide everything on the other side by 5 as well. Not just one term, everything on the other side of the equal sign. So those 5's cancel out. I'm left with y. 15 divided by 5 is 3. And 3 divided by 5 doesn't work out to anything too nice, so I'm going to leave it as a fraction, negative 3 over 5 x. Now it looks a little bit more like y equals mx plus b. Now you could leave it like this if you can discern which is the m and which is the b value, or you could rewrite it specifically to be y equals mx plus b. In this case, I'm going to take the minus 3 over 5x and move it in front. So minus 3 over 5x moves in front. This 3, there's no sign in front, so I can assume it's a positive. So plus 3 will be after or remaining. So y equals negative 3 over 5x plus 3. Now I have enough information, or I've converted it to the y equals mx plus b form. I can graph this because I know my slope, negative 3 over 5, and I know my b value of 3. So let's graph this. B value of 3 is a y-intercept of 3. Slope of negative 3 over 5 means I go down 3, so a rise of negative 3 or down 3, and a run of 5. 1, 2, 3, 4, 5. Oh, that was my x-intercept that I found previously in the first method. And if I want to, this method allows me to find other points, so I can continue 1, 2, 3 down, and 1, 2, 3, 4, 5 to the right. There's another point. And I have enough now Or I can go through, roughly draw my lines. That's not the nicest. Let me fix that. Fix the angle a little bit. And there I have my line. So two different ways that you can graph an equation in standard form, right? Whichever method is preferable to you, right? If we want to be more accurate or work with something that we're a little bit more comfortable with, we would probably want to convert to y equals mx plus b. But if we just want to get a quick sense of what it looks like, we can find the intercepts and plot those and graph it from there. Another thing that you learned with equations of lines in grade 9 are linear systems. Now, you may not have learned specifically that term linear systems, but you probably looked at two equations and compared them and find when did they cross, right? Or what was the point of interception, right? So that's what we're doing with linear systems. And this is kind of going to be an introduction to our whole first unit, which is going to focus on linear systems, finding the point of interception. So, for example, student council is planning the next semi-formal. They compare the cost of places to hold the dinner. We have Hall A, which has a $10 rental fee plus $30 per guest, and Hall B, which is a $40 rental fee plus $20 per guest. So what we want to do is basically find out, when are these two lines the same? When do they cross? Right? When will the cost between these two halls be the same? So in order to do that, first thing we want to do is write an equation for each. So for Hall A, I want something in the form y equals mx plus b. So again, we have to think about what are we looking for, a multiplier and a constant. So this per means per guest. So that means every time a new guest arrives or another guest arrives, that would be an increase of $30. That's our multiplier, right? Usually when you see the word per, that's talking about a multiplier. So we know our M value. That leaves our rental fee as our B value, which makes sense because the B value is the constant. A rental fee is constant. It doesn't change. So we have for A, y equals 30x plus 10. Now, if you wanted to, you could change the variables to make it more applicable, right? So you might have cost equals, or C equals 30 times G for guest plus 10, but it doesn't really matter as long as you're using two variables. For Hall B, y equals, again, we can see based off of Hall A, $20 is our M, $40 is our B, so 20x plus 40. Those are the two equations. Now what we can do is graph these two equations. We're going to graph these two situations. Right? So we have our y value, our x, so we have it at 0. We have 1, 2, 3, 4, 5. And we'll go up by, let's say, 20, 40, 60, 80, oops, not 800, 80, 100. We want to keep it consistent, right? You don't have to have the same increase, but we want to make sure that at least the scales are consistent for each axis. So I'm going to graph these two equations. Different ways we can do it. Right, for Hall A, let me just change the colors here. So we'll call this A. Oops. And let's do this for B. So A and B. Right, so we could, if we wanted to, for A, create a table, X and Y. So at 0 guess, it's $10. At 1 guess, it is now 40. At 2 guess, it's 70. At 3 guess, it is 100. 4 guess, it's 130. We can stop it there because we don't really, can't really go any further. Or on my graph anyways. for Hall B, so we have X and Y, so 0, so at 0 guess it's $40, at 1 guess it's 60, 2 it's 80, 3 it's 100, and at 4 it's 120. So right from here you can probably see where they're going to cross or where they're the same, but let's graph them anyways. So we have 0 and 10, 1 and 40, 2 and 70, 3 and 100. So that is Hall A. Hall B is 0 and 40, 1 and 60, 2 and 80, 3 and 100. So that is Hall B. Right, and now we can see that they do both cross at this point here at 3 and 100. And we can see that from the table as well. We see those same values coming up. So that means that they're the same values, or they have those two lines have the same values at that point. So graphically, we see that here. Again, that's what we should have with our graph, Hall B and Hall A. We see that they cross, we can see that they cross at this point, which is at 3 and 100. So in what situation is Hall A less expensive than Hall B? So less expensive costs less. Usually that means that when is the line for A lower than the line for B? We can see here it's cheaper when it's under 3 guess. Right? Anything less than 3 guess, Hall A is going to be cheaper. Right? Which doesn't quite make sense because you're only going to have 3 guess and be pretty small, semi-formal, but you never know, right? Maybe they're not popular anymore. So you're only going to have 3 guess. So if you have less than 3 guess, Hall A is less expensive. So this is an example of a linear system. And a linear system is when 2 or more linear equations are considered, or what we mean by that, tried to be solved at the same time. So we're trying to solve these equations at the same time to see when are they the same. So the main thing that we're looking for is the point of interception, or intersection. I think I've been saying interception, but it should be intersection. Spell it right, intersection. So the point of intersection of a linear system, right, or the POI, as it's sometimes called, is the solution that solves both or all equations at the same time. Right? So basically it means that those values exist in both equations at the same time. So in both equations, when x is 3, they're also 100, or y is 100. Right? So to solve the linear equations means to find the point or the values, or the point of intersection, the POI, or the values that satisfy both equations. Right? And where is that going to work? Where is that going to be? Well, that is going to be the point of intersection of the POI. We've kind of repeated ourselves. Let's change. We want to find the values. Values are really what we're looking for, or the coordinates that satisfy both equations. And again, that's going to be the point of intersection. So what we want to do is solve this linear system or find the point of intersection. So this is going to be kind of a combination of converting from standard form to y equals mx plus b, or graphing standard form. we have two equations here, negative 2x plus y equals 4, and x plus y equals 10. So different ways you can do this. I'm going to focus on converting to y equals mx plus b because that's always a good skill to have, and it does give us more information. So if we take equation 1, negative 2x plus y equals 4, and I want to convert this, I want to move that 2x plus, not the plus y, I want to move the 2x to the other side. So what I'm going to do, if I move it to the other side, it becomes a positive, so it becomes plus 2x. The 4 is still there and it's positive, so plus 4. So that's one equation. Works out nicely. The next equation, same idea. I want to move, let me just actually show what I did and move that over. Not to the 4, sorry, but on the same side of the 4. And for here, for the next one, I'm going to move this x term over to the other side. So y is left. The x, when it comes over, is a positive x. It becomes a negative x. And the 10 remains plus 10. Now that it's in this form, I should be able to graph it because I can see my m value and my b value, which will make it easier for me to graph. So I'm going to graph both of these. M is 2, B is 4, so that means my B value of 4. M value of 2 means 2, actually it means 2 over 1, so that means up 2 over 1, up 2 over 1. And I have enough points now to draw my line. So there is line 1. For line 2, it's plus 10, but my slope or my multiplier is negative 1 or negative 1 over 1, so that means I go down 1 over 1. Down 1 over 1. Continue the pattern, and we can see where they cross. We can see where they cross is right here. So that is going to be my point of intersection. That is going to be the solution for this linear system. So the point of intersection is going to be the point 2 and 8. So that is the point of intersection. Now, it does say to check. So what does that mean? Well, that means we want to make sure that that point is on both of those lines. So an easy way to do that is to plug in those values from that point of intersection and make sure it satisfies each linear equation. So for equation 1, we have an x and a y from our point of intersection, 8 and 2, or 2 and 8. So that means instead of y, we're going to write, or let me just write the full thing out. Y equals 2x plus 4. So instead of y, we're going to write 8. Instead of x, we're going to put 2. So 8 equals 2 times 2 plus 4. 2 times 2 is 4 plus 4. 4 plus 4 is 8. 8 does equal 8. So this works. This point is on that line. It satisfies that equation. Now, we can't just do one. Point of intersection means that it's on both lines. So we have to check our second equation as well. Y equals negative x plus 10. 8 equals negative 1 or negative x, and x in this case happens to be 2. So it becomes negative 2 plus 10. Negative 2 plus 10 is 8, so 8 equals 8. Left side equals right side, or 8 does equal 8. So that works for that equation as well. Now, you could have used the original equations, plugged in the x and y. You didn't need to use the converted ones. But because they're the exact same equation, just written a different way, it shouldn't matter. Remember to make sure you check both equations because to satisfy the linear system, means it needs to be the point of intersection, which means the values have to be on both lines. So that is kind of what you looked at in grade 9 in terms of linear systems. Maybe not so much. This last example may have been a bit more of an extension on what you looked at, but in terms of graphing lines and finding where they cross, that you should have done in grade 9. The checking of the points, you've checked points or checked solutions in for equations. Very similar idea when we're checking if a point's on a line, if you didn't cover that in grade 9. So again, make sure you are practicing to kind of review in terms of graphing lines, finding the linear or finding the point of intersection, understanding what the equation of a line tells us in terms of y equals mx plus b, and even seeing the application of linear systems.